What do you got?
When you turn off a light, does it stop the whole? I don't know how to explain it, but like, let's say you have a laser and it's shooting out a beam of light.
Mhm.
When you turn off that laser, does the beam stop immediately, or does it like?
So what's already been emitted is still there,
Okay.
but it's moving so fast you can't.
Okay.
So you know how like in Star Wars when they shoot,
Ooh.
it's like a.
Yeah.
Who saw it? Did you see? I think it was The Force Awakens.
I think so.
Kylo Ren froze the beam, the blaster beam
Yeah.
in the air, and it was just going zzz, like sitting there. It was like
Yeah,
a,
oh, yeah.
yeah. So that's what I think would happen if you could see it.
Okay.
Does that make sense? So if
Yeah.
you shut it off, you still have what's already been
So it
emitted.
just stays in the air.
Well, it's going somewhere, but yeah, it would. Yes, if you could, yeah, like a high-speed camera, take a zillion pictures of it. Yeah, you would see it frame by frame moving.
Okay.
I think that's. Yeah, because it's got to come from the source, and then if you shut the source off, the light that's been emitted still exists.
So,
So,
it'll still be.
I
Okay.
I
Would
think
it keep
so.
moving though?
Yeah, it would.
Okay.
Yeah. I mean, the movie he was using the four, that obviously doesn't exist, but it's not that we know.
Does it?
Hey, it's in a galaxy far, far away, so.
That's true. It
might-
could be in a different universe. There's multiverse theory.
Wait,
You
if-
guys talk about that at all in astronomy?
If-
There's like different universes. Like there's a parallel universe where all of our twins are there doing different
Oh yeah,
things.
just
Ooh.
did you hear? Do you know the theory? Do you know the theory how like say we're like 3D and everything, and then there's a 4D
Right,
figure, and we can't see them, but they can see us.
Right, and then it goes up.
Yeah.
Yeah, there's
And-
like 12 dimensions or something.
Yeah.
More.
That's
I
what
swear.
We are the Sims.
If,
So-
if it's a parallel universe,
Like,
does
what's
it
changing
care
like
about
that?
physics too?
Well, there's other universe they claim that physics here doesn't apply there, like time. Time can be manipulated as a physical thing. Here it can't be. We gotta move on. I'll get going on that. All right. Now, nuclear chem. All right, nuclear chemistry. What did we write? Anything?
Nucleus, protons and neutrons, stable and unstable.
Okay, good.
Radiation on top.
All right, good. So, one thing that I want to get some basics down today. What creates radiation? What makes an element radioactive? Because that's what nuclear chemistry is all about. Did someone just raise their hand?
Who?
No? Oh, someone raised their hand. So let's write this down here. The reason atoms, sorry, not atoms, some atoms are radioactive, and we're going to define radioactivity and radiation today. The reason some atoms are radioactive, and by the way, these atoms are called radioisotopes. Radioisotopes. So the word radioisotopes means it's an isotope of an element that emits radiation. So most of those elements up there are not radioactive, but their isotopes are. I'll explain that after this definition, or after this sentence here. The reason some atoms are radioactive, they're called radioisotopes, is due to having an unstable, Shane, did I start that?
Yeah.
Okay, an unstable nucleus. And underline that. That's the whole key. That's the whole key. So, the nucleus of radioactive elements just can't hold itself together. It's unstable. So it starts losing some of itself in the form of radiation. That's really what it's all about. That's a very simple way to explain it. The reason some atoms are radioactive is due to having an unstable nucleus. And an unstable nucleus means the neutron to proton ratio is not, capitalize not, underline it, 1 to 1. I'm going to show you a picture here in a little bit. It's called the belt of stability. All the elements up there that have 1 proton for every 1 neutron, or 1 neutron for every 1 proton, is extremely stable, not radioactive. The further away you get from that 1 to 1, so the belt of stability, don't draw this, you can just look up here. So here's a 1 to 1 ratio. If here's protons, here's neutrons, this is 1 to 1. The belt of stability starts out on the line, and then it gets further and further away, the more neutrons you have. So the bigger the neutron number gets, the further from that 1 to 1 and the more unstable it becomes. So if you look at uranium, number 92, it has way more neutrons than, let's say, carbon. Carbon has 6 neutrons and 6 protons, so it's way down here. But uranium is up here somewhere because it has so many neutrons, it's much further away from that 1 to 1 line. Yeah.
Do like radioactive and radioisotopes have anything to do with radio waves?
No.
Or that's
Nope.
happen to have the same name?
Yeah.
Okay.
Yep. So, good question. In fact, radio waves aren't emitted from nucleus. Nothing to do with this stuff.
Okay.
So, it's really just those 4: gamma, alpha, beta, and positron. So, we'll show you that picture in a little bit. But that's the whole key. All right, and that's what your homework kind of stresses a little bit. Anyone have the homework handy? I don't have a copy.
No.
Oh, yeah, right here. See that line right there?
Yeah.
That's that line I just drew.
Okay.
That's the 1 to 1. Okay? So anything not on it is not going to be stable, which means it's radioactive. All right? So that's like the biggest thing I want you to learn today. What causes radiation, radioactivity? This unstable nucleus, and it's because the nucleus is kind of, I don't want to say screwed up, but it's not comfortable. It wants a 1 to 1. So what does it do? Yeah. What does it do?
What do you mean?
It's
What do you mean?
things.
What is it?
How does it fix itself? Because the nucleus wants to be stable.
It
So
gets
what
to
it,
go down to lose energy, go to the ground state.
well, no,
Like-
hold it.
Use nucleus.
Everyone stop, stop. I gotta
Rolling
fix
up.
this. What particle does what you just talked about? Go ahead.
The
Right,
What's that word mean?
nucleus.
right.
Oh, protons.
Protons, neutrons, electrons
Oh.
have nothing to do with any of this.
They get.
So I just want you to realize
Yeah.
it so that you understand. I'm not picking on you.
They
Okay.
get more radiation.
All right. Jake, what were you saying? How do these things become stable?
They get rid of the radiation.
They get rid of radiation. You ever hear of half-life? Yeah, I brought it up. Go to table N.
Not again.
Guess how long it takes uranium-238 to become stable?
What?
Find it.
4.47 times 10 to the 9. Why?
4.5 billion years it takes for uranium to emit enough radiation where the nucleus is now stable. 4.5 billion years? What'd you ask me?
How old's the Earth?
Oh, the same.
Okay.
Yeah.
That's what I thought.
Yeah, uranium's natural, and we are, it's a finite amount. Once we run out of uranium, that's it.
Oh
Okay.
no.
And since a lot of the uranium was created right around when the Earth was formed, because of all the heat and pressure, everything that was happening, the chemical reactions, all the uranium was formed back then. So now it's gone through almost a half-life, which means only half of it's left. But anyways, but look at carbon-14. Carbon-14 is radioactive. Go to table N, find carbon-14. 5,715, right? So it's it's still a long time, but it's way less time than uranium.
Relatively not a lot.
So francium takes 27.4 seconds.
There you go.
Yeah, I saw that.
Right, some elements, as soon as they're created, it could be artificially, it could be naturally, in natural process. And I don't know how all these things are created naturally,
16,
but yes, as soon as they're created, they basically start to break down and give off the radiation. Yeah.
So calcium-37 is 182 ms. Is that milliseconds?
Yeah.
Damn.
That's really fast. Right. So you're starting to see there's a huge difference here. But the point is, once they've gone through a whole bunch of half-lives, they're basically stable now. But what did I tell you yesterday?
That they're not what they used to be.
Right. They turn into something new. So I'm kind of
Wait,
saying everything.
How
Hold
is
Go
like
ahead.
3.823 days?
Days.
How is it like a decimal not?
Because then you can break it down to hours, minutes. They're just keeping it as days to make it easier. Instead of saying 3 days, 12 hours, 6 minutes, or whatever, that would be like crazy. So they're just keeping it in
Okay.
days. So I'm saying a lot here. Hope you're following most of it, but let's take some notes kind of slowly here. So underneath what you just wrote, write this: the radioisotope will emit radiation from its nucleus in order to become stable. So those two phrases or those two lines in our notes are probably the most important thing to learn today. Everything else is kind of lost or forgotten. Not that big a deal, but these two things. What makes it radioactive, and then what does it do to become stable? That's what it does. It emits alpha, beta, gamma, positron. And at different elements emit different types of radiation. The size of the atom factors in. All the big ones tend to emit alpha, and the little atoms tend to emit the other ones, gamma, positron, and beta, which makes sense. Because if you have a really large atom, it has a lot of mass. So it's going to emit radiation with a big mass. The little ones don't have a lot of mass, so they're going to emit radiation with hardly any mass. So, the analogy I use, and I think I brought it up yesterday, if you're sick to your stomach, okay? Really, upset stomach, right? What do? Your body sometimes forces you, you're like, oh, I gotta throw up. You throw up. Now, you're supposed to feel better, and maybe not immediately, but usually if you throw up, you do feel a little better. So our throw up is our radiation, okay, for the analogy. And you'll feel better afterwards, you'll feel more stable. So that's kind of how I talk about it. The radioactive atom is sick, and it wants to become healthy. How does it do that? It throws up. It gets rid of radiation. Now, it gets a little silly. So uranium throws up for 4.5 billion years, okay? And that's kind of crazy, right?
How do you have that much food in your stomach?
If you throw up more than a couple times, there's usually you should probably go see a doctor or go to the hospital. If you're really sick, sometimes it's a lot of throw up. That's a big problem. So, but obviously it's just an analogy. Here, it can take a long time. It can take milliseconds. Okay, so that's the key. So hopefully, if they get enough out of their nucleus, the ratio starts to come back to 1 to 1 or closer. All right? Yeah.
How does getting rid of radiation equal the proton-neutron ratio?
And there, my friend, is the magic. And that's what makes it nuclear chemistry. So, when one element emits, let's say, a beta particle, a proton just magically appears in its place. So a nucleus gets rid of an electron. One, how the heck did the electron get in there in the first place? And two, where did the proton come from? That's nuclear chemistry, and that's quarks and lepton, all the smaller subatomic particles that make up subatomic particles, they factor in that.
Do you know the answer to that?
Yeah, it's because the quarks, it's like 3 quarks make up a proton and a neutron, but you need like 2 ups and a down for a proton and 2 downs and an up for a neutron. I forget exactly what it is. So anyone watching this, I might be wrong. But when you emit a beta or beta radiation, the quarks change, and then therefore you have now a proton. So there is an explanation, but you have to keep working backwards into smaller particles. I don't know it exactly, but that's the gist of it.
Wow.
So, all right. So, a couple more definitions here. So, what is radioactivity?
Radiation.
The amount of radiation released by
It's the process of releasing radiation. Process of releasing radiation. That's all. So if something's giving off radiation, that's called radioactivity. Radiation is a particle or wave emitted by a radioisotope. And I already talked about the 4 types. We're going to take more notes on those on Friday. I need right to the end here because I got to explain one more thing. But that's what radiation is. Radiation is the alpha, beta. We can write them down. Alpha, beta, gamma, positron. All right. Now there's one more thing I got to show you. And it's called natural decay or natural transmutation. I'm going to say natural transmutation. There's actually three ways to say it. Radioactive decay, radioactive transmutation, natural decay, natural transmutation. I'll write the other ones down tomorrow or Friday. But I want you to get an example of this. Okay, here's an example. Take carbon 14 over 6. Carbon 14, that's on table N. You find carbon 14 on table N. What particle does it emit? Beta. So I'm going to draw an arrow, because this arrow means this is emitting. 0 over negative 1e. There's my beta particle. So when carbon 14, it's unstable because it's not a 1-to-1 ratio, it's 8 to 6, 8 neutrons to 6 protons. When this emits radiation, it's like throwing up. Well, here's the weird analogy. Let's say Quinn is really sick, goes in the bathroom, throws up, comes out of the bathroom, he turned into Will.
Whoa.
Whoa, whoa.
So Quinn goes in, Will comes out.
What's the difference?
Now, let's say Kaylin throws up. She's in her bathroom, throws up, comes out of the bathroom, turned into Dr. Peterson. Oh, all right.
That's really creepy.
Okay? That is transmutation.
But-
You're interrupting my class. What's transmutation? When one element
Becomes
turns into a complete. Hold it. Don't move. Give me 30 more seconds. Turns into a completely different element. Look up here. What number plus 0 equals 14? 14. What number plus negative 1 equals 6? 7. Who's number 7? Nitrogen. Hold on. 10 more seconds. When carbon throws up or emits radiation, it turns into nitrogen. Carbon is no longer there. That's what transmutation means. You needed to know that one little thing there to finish your homework. All right? So we'll talk more about it Friday. Don't forget your